Hi, class. It is time for the last lecture of Chapter 6 in Geological Processes, Soils, and Minerals. And today we're really going to be focusing on soils and the mining part of minerals here. And I'm on my iPad today, so it'll be a little bit different. I can zoom around like this, and I can draw as much as I like. So let's get into it. So going through Chapter 6 here, we've gone through elements of the Earth's crust, tectonic plates, how that creates volcanoes and earthquakes. We've just gone through the rock cycle where pretty much all rocks come from and where basically where all soils come from are from those rocks. And now we're going to talk about different types of soil, how they're formed, their characteristics, and explain how and why we mine minerals and some of the effects on the environment they have. So let's first talk about soil. And it really does. It links that underlying rock cycle with all the human biosphere. So it's like eroding those huge pieces of rocks into the soil, into the pieces of rocks that we typically interact with, which is the smaller pieces of soil. And soil really is a mix of geological and organic components. So living and non-living. It's a mixture of those two, depending on the ratio. It's all mixtures, but different ratios. So we're going to go through a photo of these, but first, probably some obvious importances of soil, but we're going to go through all of them briefly. First of all, it's a medium for how our plants grow. It also is a very important primary filter for water. So water percolating through and down through the soil, it gets filtered. It also is a habitat for many living organisms. That's an understatement. It is the place where organic material is broken down and we can actually recycle nutrients. So nutrients will be used by us and by animals and they'll get broken down. Leaves use nutrients, they'll get broken down by organisms, so we can recycle those back into the soil. It also serves as a filter for pollutants. So water and in general pollutants. So really important aspects of what soil does. This is figure 6.19 from the book and it just shows you some of these processes. So we've got these different layers of types of soil, but first of all, we've got our plants growing. It filters our water, habitats for organisms, ones that we can see and also ones that we cannot see. And then this process of recycling organic material. So these leaves break down and die. These get decomposed by organisms. Then more plants can use those and grow. So this recycling system for nutrients. So how does this soil form? Where in the world does it come from? Well, first of all, it has some sort of parent material. So we talked about different types of rocks that came from the rock cycle. So igneous rocks from lava. Maybe those rocks were then combined with other types of rocks and weathered and all this kind of stuff. So the soil has to come from some parent material to begin with. So there's got to be a parent material, and then it's formed in a specific type of climate that can influence the type of formation. The surface and slope of where that soil is can influence the type of formation that happens, so the topography. The different organisms that end up their way in the soil, that has to do with a lot of type of composition that soil is. And then also the time, the amount of time spent that soil had to form. So all of these, the parent material, climate, topography, the composition of the organisms, and the amount of time taken really give you the formulation of the soil that we're talking about. So when they start to layer down on top of the earth, we talk about them in layers or we call them horizons. And they have these characteristics layers we can recognize in different areas of the world. One is where all the action is in terms of animals and plants and things dying and things decomposing. We call that the O horizon or the organic horizon. A is our topsoil part versus the subsoil. So this is where we get a mixture. So this could be some sort of mixture of organic material and then more mineral material. Think more minerals, pure minerals down here. And as you go upward, you have more organic material. So living things and then minerals as you go up the horizons. B horizon, this is where a lot of the metals and also nutrients accumulate. Less organic material, but maybe some. Notice it says in some soils an E horizon occurs beneath either the O or the A. So sometimes we actually have another kind of variation, but these are the four basic ones we're going to be focusing on. And then the C horizon, this is the least weathered portion. It's really mostly that mineral chunks, tough material, and it's similar to the parent material, or mostly similar. So as you get higher, looks less and less and less like the parent rock material. These are the more formal definitions, a little bit more information of what I just talked about. So the organic layer is the O layer. Some of those things you can think of are things like leaves, needles from pine trees, twigs, also animal bodies, insect bodies. So a lot of stuff that dies and falls to the surface of the forest, for example, that would be your small organic layer, really rich in organic material. And then the A horizon is really what we call the topsoil. So organic layer is different than the topsoil. This is less like soil in my mind. This really becomes starting to think of soil in my head. So it's a mixture of organic and minerals. It's a really good mixture for growing things. Notice we've got all these roots going through the topsoil and then ending when you get to that subsoil. So horizon B is where we start our subsoil layer. It's mostly mineral with a little bit of organic material. And then horizon C is that really parent material layer, not weathered, very similar to the parent material. So that's how we classify the different layers of these soils. Now, we haven't talked about composition. So there's a lot of different types of soils. The types of soils may follow similar layering, but the composition can be very different. So we like to look at the texture. The texture of the soil gives us a lot of information on what's inside it. So we have these percentages of sand, silt, and clay. We're going to define all those and show their sizes here. Here is the soil scientist probably best friend in terms of just talking about general composition. We use this texture chart over here. So, and maybe before we get into the texture chart, let's look at part B of this figure. It shows the relative size magnified approximately 100 times of what these particles might look like. Notice sand, it looks massive, like the surface of the earth, and this is like the moon or something, but it's magnified. So to see clay, that's less than 0.002 millimeters. Silt is pretty small too, but much bigger than clay. And then sand is way bigger than either of these two. So that depending on the type, the composition of sand, silt, and clay, we classify different soils depending on this composition. So the example it gives you, if you want to dial in on what we call loam, loam is if you take something like 40% sand, so pretty good amount of sand, and also 40% silt, and then only 20% of the really tiny clay particles. That would tell us we're at the loam type of soil. And notice we have different classifications of loam. Loam really kind of sits on this line here, this area. If you have more silt, notice, let's say 70% over here, 20% clay, and 30% sand, that would be, that would be 10% over here. It has to add up to 100, now doesn't it? That'd be more of a silt loam. Over here, we have a line between sandy loam and sandy clay loam. If you go north and to a little bit, when you have 30% more clay, or 30% of clay instead of 20, you would call it clay loam. So this is the type of soils that we classify these in. Sand would really be almost 100%. Silt is almost 100%. And to call something clay, well, there's a kind of actually a pretty large section here. If you have 70% clay and 80% clay already, and let's say 10% silt, we still pretty much just call it clay. It really overtakes the characteristics of the soil at that point. So what are the importance of these different types? Well, the type of plants that grow in it, the area of the world, you might have different compositions, and then really water. How well does water filter through here? This is figure 16.23, and it shows the drastic difference between your type of soil and how long it takes water to get through there. So the porosity. This has the highest porosity, and this has the lowest. Relative to each other, let's say this is some quantity of water and this is some quantity of soil. If it's 100% sand, it would take about an hour. Silt, 100 days, very significantly different. But look at clay, 100 years. So you can be, if you have 100% clay beneath you, that's almost like a permanent spot you could build something. Not quite, but that's really packed in. Those particles are so small that the water takes so long to get through there, really low porosity. Now the book makes a note that the best agricultural soil is a mixture of sand, silt, and clay. So that promotes good amount of retention. So mostly sand provides poor retention for the roots. But if you mixture, the roots can grab onto things, the plant doesn't fly away and push around. So the plant needs somewhere to grab into, but it also needs decent amount of drainage. So a mixture of these is the ideal situation for great agriculture. And I made a note here. This does not mean you're going to naturally find sources of soil like this all over the world. So it depends on where you live, with the composition, the topography, the climate, etc., where you're going to find these types and compositions of sand. So what in the world is inside the soil? Well, regardless of what type of soil, if we go back to here, remember there's a lot of organics in here, especially when you go outside and it's going to start digging into the O horizon. Maybe you get down to the into the topsoil as well. There's a lot of organic material in here, a lot of living organisms that live here. So if we go back to this slide, this is just a few of what you might find in there. So we have large things like worms, slugs up here. We also have, large creatures that burrow their way through here. And we also have millions upon millions of bacteria and protozoa, fungi that are some you can see, some you can't see. And this figure notes that between 80 and 90% of soil organisms are bacteria, fungi, and protozoans. So most of the living stuff in that soil are things that we can't even really see. So when you go out and scoop a thing of soil in your hand, it's teeming with life, even though you might not think so. There are a lot of organisms that are living in there, and the ecosystem depends on this relationship between the organic materials up top coming in here and recycling through the process of organisms breaking them down. What can happen though if we overuse the soil? So this is kind of bringing it back to the human use. This is showing some erosion from too much farming. So if we overuse the soil and we don't replenish it with nutrients, or we don't replenish its structure again, if we pack it down too hard, or we till the soil too much and we lose the composition, the natural composition, you can lead to degradation. So that's the loss of some or all of the ability of soils to support plant growth. So you can mess up with the composition, so you don't get as much retention and the correct drainage anymore. You can also deplete it of its nutrients. So we can do that by just overusing, over-irrigating, or also the application of pesticides. They can pollute the soil, and now it's not a situation where all those teeming with life and organisms can actually live anymore. So point of this is soil is very important, and we need to use it wisely. So that is the first part of our section, all about soil. Where does it come from? How does it form? What do the parts and layers look like? What types of soil look like what? And now we're going to move on to mineral resources. So this is the big key point of the next section. It says the unequal distribution of mineral resources has social and environmental consequences. Very true. We don't find all the gold in one spot in the world. We don't find an even amount of gold, an even amount of copper. There are pockets of this stuff all over the world. And if a lot of countries have one resource, they kind of have a monopoly on that resource. But let's just talk about some of these mineral resources in general. So in terms of just the overall composition of the Earth's crust, most of it is oxygen and silicon. Oxygen in terms of oxides, so iron oxides. So rust, for example. Metals on their own are fairly, for the most part, pretty reactive. Gold and silver, platinum, these do not form oxides very easily. So they actually are in the earth straight up. Copper does form oxides, but you can also find some pure copper out there. But these are really the ones you would find pure, but most of the time we find metals in oxides. So silicon, SiO2, basically all that sand that we see on the beach, all the sandy material, it's mostly just silicon dioxide. So most of the material in there is silicon and oxygen. We have a bunch of aluminum, decent amount of iron, magnesium, calcium, and then this big other. This is where a lot of the valuable and materials that we don't have a lot of are. Now, what happens when we run out of this stuff? Well, when we run out of this stuff, it's gone unless we're able to recycle it somehow. So the book notes, and this is from 2007, so I'm not sure how much it's changed now. Now the reserves, this is the definition of and I added, this is also from the book though, but publicly known quantity of a resource that can be economically recovered. There are a lot of private companies and private people that have resources that haven't been accounted for. So it's difficult to really know how much of this stuff is left. But these are some of the publicly known quantities of global reserves versus US reserves, the sum of these really important metals. And we notice even iron, the US has 40 years of iron for our whatever we would use it for. The globe has 120 left. Aluminum, there's quite a bit left. US has very little left though. And notice down here, there's 4 elements down here, 4 metals, nickel, cobalt, magnesium, and chromium. The US doesn't have any left. We don't have any known public reserves of nickel, cobalt, magnesium, or chromium. So any of these we have to import from other countries. A lot of economical and political ramifications for the uneven distribution of resources around the world. So how do we get these resources out of the ground though? Let's say we have some of this copper and lead to grab. Well, there's a few different types of ways to mine it that we're going to talk about. I'm going to spend some time looking at some pictures of some big open pits. So these we just start going deeper and deeper and deeper and working our way through the material and making roads all the way down to the bottom. There's also mountaintop removal where you just start exploding huge chunks of mountain. There's strip mining where we're taking the surface, or really more of a surface removal, little bits of surface at a time. There are subsurface. This is the classic going down into a mine shaft and building tunnels. And then placer. This is where you would see people panning for gold, or also using different mechanisms for taking sediments out of riverbeds. And gold is typically used, or this style is typically used to find gold, although there's plenty of open pit mines for gold as well. Gold in this case is very heavy and it settles out to the bottom of the water. So let's talk about these a little bit more. Strip mining removes strips of soil and rock to expose the ores beneath it, like the iron oxide ores. And we call the waste that are produced tailings. So kind of like you strip it, take the oxides and you push the rest over onto the side and you've got these large areas of tailings. Open pit mining is a very common one as well. So you just keep going down and down and down into a hole and it leaves this massive open surface. We see a lot of copper mines they happen to be an ore the copper is actually a metal that happens to be at these levels where we can just drill down and grab it off the sides of these holes. And I was curious what some of the biggest ones in the world were and that type of thing. This is one of the biggest ones in the world. It's hard to tell how big this is, but this is Bingham Canyon Mine. It's right outside Salt Lake City. You can probably see some of the city up here. This is 3 miles wide and a mile deep. I can't imagine what this might look like. This probably looks like the Grand Canyon or something. So this is a massive, active, open pit mine. These are roads. If you want to get down there, you've got to take this road all the way down. It's a long trip. And when they do this, you have constant trucks that are spraying water all over the surface to keep the dust levels down. And you got the trucks bringing the material back up to the surface to crush and process. So it's a constant digging and taking out and spraying water down type of process. I actually looked this up on Google Maps because I was curious. And here's Salt Lake City. And here is the Bingham Copper Mine Complex. So this massive, massive, massive place is right over here. Notice like this is 3 miles. That's like a huge chunk of city's worth of room there. So there's the Bingham Copper Mine. One that I'm very familiar with is the Berkeley Pit. So this is now a Superfund site. We talked about that in one of our chapters, as in this is national money from the EPA is being used right now to help clean this up. This is a massive pit. So this is Butte, Montana. Notice here's the city over here. Lots of houses and parks and a stadium, a football stadium, and then the pit. It's just a massive, massive open pit. This over here is called the Yankee Doodle Tailings Pond, pond or something. This is tailings from this operation. So all the junk that they didn't need and didn't want from the processing, and it kind of settles down in here. And this is a dam here, keeping all of this water up here. And you notice it's actually quite blue and actually gets pretty clean down to this area because these tailings only fall about here. So the pH over at this side actually isn't bad at all because there's not a whole lot of heavy metals over here. This is where all the heavy metal waste is. So leached out of the sides of the pit. This is a non-operating pit, so they don't have water pumps in the bottom anymore. So the groundwater comes back in from the water table and seeps in. And now it is completely filled with acidic, toxic water with dissolved metals. So very large environmental hazard that they're trying to clean up right now. And I got some other pics as I was curious. This is 1984, I think maybe a year or two after they closed it. It already started to be filling up with water. And now this is in 2005. You can see almost completely filled to the top with water. And it's acidic, full of dissolved toxic metals. And this is a beautiful photo I found of it. But again, you can see how full it is next to the city of Butte. So I actually did a project trying to clean this place up, or at least, develop technology to. So there's a college in town, Montana Tech is in town, and I got my PhD in Bozeman, Montana, and I was doing a postdoc research position in Missoula, Montana, and I was helped creating nanoparticles that would go into here and grab the metals out of the water. And they were magnetic, so we could use a magnet to extract them. So extract the particles and then strip the metals off and then reuse them was the key. So there's still a lot of work and projects being done to try to clean up all the waste in this open pit mine here. Big problems when they fill up with water and they just sit there and they can leach into your water system. So those were, let's see, what did we just go through? We went through strip mining, so removing the surface, and open pit mining, kind of digging straight down to the holes. These are the two types of surface mining. And then there's also mountaintop removal. This is another type of surface mining. You're literally taking chunks of mountains apart with explosives. And then placer mining is when you're in the rivers searching for sediments. So gold is often recovered. So sediments and rivers. Then there's subsurface mining. So this is 100 meters or below the earth. And there's a lot of pros and cons of surface versus subsurface. So if you notice, there's quite a bit of effects on the air, effects on water, effects on soil, biodiversity, and then the human effect. In terms of the human effect, surface mining is minimal human effect for the people actually working there, but air quality and water quality, like we see with the Butte, Montana mine, can affect those surrounding the mines. Subsurface, there's a lot of hazards going into the people actually work there, but less so for the people around the mine. And you notice surface mining, a lot of dust is a problem on the air. Subsurface, not so much, but they use a lot of fossil fuels to actually dig. Surface mining, easily contaminate water through tailings or open pits. Subsurface mining, you can also get that through the using acids to mine some of these and dissolve some of these metals, so that can also percolate through the tailings. No real surface soil effects for subsurface mining. The only subsurface mining effect for biodiversity is really road construction. And there's quite a bit for surface mining because you can really heavily alter the areas for that. So in general, surface mining is more damage to the environment, but subsurface mining is more significantly dangerous to the actual miners. And this is interesting. In general, mining legislation does not address environmental issues, with the exception of coal mining. There are not many regulations out there that tell mining companies what to do in terms of what they're doing to the environment. So we end up with these Superfund sites after these companies just leave their mining sites sitting there, and then it becomes an environmental hazard. However, there are some rules in place for coal mining. And the last piece of the chapter goes through this reclamation idea. Coal mining, there are some rules in place for coal mines they actually make them turn their land back into a livable habitat. The Trapper mine in Colorado is one of those that's used as a case study as a really good example of it. They're apparently very meticulous in keeping all of the topsoil and all of the soil that they pushed away, and then putting it back once they're done. So this is an example of when they were actively mining versus when they were done mining. They put in all the topsoil that they pushed out of there, and then replanted and created it as a living habitat again. So that's what mining companies are supposed to do if they're coal mines, like the Trapper mine. But there's really not a lot of legislation forcing other types of mines to do that, which, in my opinion, is too bad. So that is the end of chapter 6. And I have all the review questions in the back of here. I'll go through these each just for a second so you can see some of these. This is from the first lecture. Also from the first lecture, what a fault is, where do earthquakes occur, what is an epicenter. We have the Richter scale question. This is kind of like pH, remember. The magnitude is logarithmic. What are minerals? Why do volcanoes occur? Then we had the rock cycle, the different types of rocks, how they're formed, types of weathering, erosions, and then we talked about soil, types of soil, particles in there, what are the soil horizons, and then different types of mining. So go through these on your own. I'm going to post this to the course website, and I'll see you guys next Monday.